Welcome back to 441A, 541A. Hopefully things will proceed okay. A little nervous, but deck chairs have been rearranged, haven't they? We have a place to play here in the room, but I think everyone is oriented okay. What I want to make clear is that there will be special office hours before a lot of things are due. A lot of things are due on Wednesday of next week, and I'm going to have some special office hours on Tuesday from 10 a.m. to noon before my calendar gets all filled up. I thought I would put that in, so if you want to ask questions, there is time on Tuesday morning in the normal location for office hours. What will be coming due on Wednesday of next week is the lab number 3 submission into the Dropbox. Your project, if you're in 541A, that needs to be finished. There is some additional material on D2L talking about how do we calculate these gain constants. That follows lecture 9.1, and I'm calling it 9.1E for extra. There's something that follows the last lecture that we had, which was lecture 9.2, dealing with phase lead design using Bode plots, and that's now with more MATLAB, so I'm calling that 9.2M for MATLAB-based phase lead controller design. Those skills will be checked in homework number 9. That's where you're going to be doing your Bode plot based controller design strategies, and that's due on Wednesday, as is the state space design, which hopefully that won't take a lot of work, especially after today's discussion in class. Teacher course evaluations are due also on Wednesday of next week, and hopefully you have the link to that, and you're probably receiving reminders, and I've commented on how that is used. That feedback is used to help improve the air between the ideal material in class and where it actually might be. We all know about feedback. So I would correct, hopefully, based on what feedback is provided or input is given in the TCEs. The final exam is on Tuesday, the 11th of December, and that's from 10:30 to 12:30. Today what we want to do is get into Chapter 11, which is full state feedback design. If you want to, you can think about lab number 2. Lab number 2 was actually using full state feedback design. We were emphasizing locations in the complex plane where our closed loop poles were located, but in fact we were using full state feedback design to make that happen. There we were assuming we had not only the position of that mass available to feedback, but also the velocity. Those are the two state variables. The full state was available to us in lab number 2 to allow us to essentially move the poles, the closed loop poles, wherever we wanted in the complex S-plane. We're going to work through a full state feedback example. We'll look at the block diagram, and we'll see how we can actually use more than just the state information. We can also apply, through our input, a reference input. Our full input into the system will consist of state variables being fed back, scaled and fed back, in addition to the reference input also being weighted and fed into the input to the system. So let's start with full state feedback, Chapter 11, and really we're sort of saying what is possible, and in this case we're going to see that it's maybe easier to design for particular closed loop pole locations. And the reason it is easier is now we're assuming we have access to much more information. Now we're assuming we have the entire state vector x that we can measure, meaning our output measurement system would be the identity matrix, is one way to think of that if you wanted to think of it in terms of using outputs to feed back relative to comparing that to what we've been doing recently, where we just assume we have a single output signal and we have to then determine or design our system based on having that one signal available to us. Here in Chapter 11, we are assuming, we're making the assumption that we have all of the state variables available and we can adjust those and feed those, use those to influence the input into the system. We can now make u of t a function of all of those state variables. If you now have this system, x dot equal ax plus bu, x I'm saying by this notation that it is an n-dimensional vector. In Nevada might be 10 state variables. We might have m Michigan inputs, u, where m might be 4. We might have 4 inputs and 10 state variables, where little n is 10, m, the number of inputs, is 4, just to give us something to think about relative to the sizing or the dimensions of these matrices. If I ask you, how does this system behave? If I gave you A and B, what could you start to tell me or describe or start calculating if I said, how is this system going to respond if I walk up and kick it? How will it perform? And how could you tell me how it would perform? When I say I walk up and kick it, I'm not trying to be mean, but I'm trying to what? Find out its dynamics. How does it behave? How does it shake? How does it move? What part of A and B would tell you something about the system's dynamical behavior? Have we talked about that at all or not? If not, let me say, what is influencing the open loop dynamics? Let's just say there's no input applied, no u. You just walk up, or you now establish some initial conditions and you say, okay, respond to these initial conditions. What's the system? How is it going to behave? What are its open loop dynamics? That's equivalent to you now going over to the math department and calculating the eigenvalues of that A matrix. If you find the eigenvalues of that A matrix, that now tells you where the poles of your open loop system are, or that now governs your open loop dynamics. The open loop dynamics then are the eigenvalues of what we will call the system matrix. That's A. And I might denote that as lambda of A. Lambda is then this function that produces the eigenvalues. What we want to think about today is in fact modifying or changing or adjusting those open loop dynamics. How can we make the system behave differently if we're not happy with it or we want it to move or respond in a different manner? And in this class, since it's a controls class, we're assuming we're not going to go in and rebuild the system, change the A matrix that way. We're going to apply feedback. And the feedback that we will use is, we said it's full state, so that means that we have the entire state vector x available to us. We're going to now weight each of those through this matrix K, and if we wanted to push the system in a particular direction, let's assume that we also have a reference input available to drive the system how we want it driven. X of t is our full state vector. and R of t is what we will refer to as the reference input. And to get us thinking dimensionally, suppose that I now said, okay, here is u. This is now equal to a minus k times an x plus an n times an r. And why did I space them that way? I want to emphasize that these have shapes other than just scalar quantities. X is a vector. If x is a vector, what does it look like in terms of its dimension? Let's say that we sketch it that way, meaning it's one column, and how tall is it? Let's say that we now, in this example, let's just assume that x is lowercase n by 1, or Nevada components. We said n is equal to 10 just to give us something to fix on. U, our number of inputs, let's say that that is M, Michigan, and let's say that R, I guess I went a little bit down in states. Now this is Pennsylvania, so I go a little south and east. So I'm going across the United States from Nevada to Michigan to Pennsylvania. Okay, the state vector has n components, the input has m components, and the reference input has p components. How do we now draw rectangles around u, k, x, n, and r to make this equation consistent? U is a vector, so we know that it is one column wide, but now we're saying it's m column or m rows tall. U is now m by 1. To be consistent or to be compatible, and x we just said has n rows in it, and it's one column, and r, just to be different, let's now see if I can draw this a little different than m. That's now one column wide, but it's p rows tall. Those are given. M, n, and p are given. Now it's simply remembering how to multiply matrices in order to make this equation consistent or compatible. The left-hand side has m rows. That means all the terms on the right have to be consistent. They have to have m rows as well. And how many columns are on the left? One column. Well, x is one column, r is one column. That's going to happen if we can make k compatible with x and n compatible with r. Is it clear what I'm trying to say? What are the dimensions of k, the full state feedback gain matrix, the way I've now defined the dimension of u, x, and r? It now has to have as many columns as x has rows. It has to be n columns wide, and it has to be as tall. I didn't draw it consistent with u, but it has to be as tall as u. It has to have m rows and n columns. So now you could say, based on that given information, k belongs to, let's say, a real matrix that's m by n in size, or its dimensions are m and n. Similarly, how do we now create n, or dimensionally create n? It's now m by p. It's now p columns wide and m rows tall, or n is now m by p. On the final exam, if you're asked a question and you start giving me incorrectly dimensioned k's and n's, I'm going to just start deducting points, right? So don't allow me to deduct points by getting those incorrect. But now that tells you how many elements are in K and how many are in N that you have to find. We now want to close the loop with our feedback. Meaning, if I now have my system dynamics, x dot is ax of t plus b, and now I'm applying u equal to this right-hand side. U of t is now minus kx of t plus n r of t. And that minus is not subtracting from k. I hope that's clear. That's a scalar. That's just a minus 1. Maybe, is that confusing? Can I just say this is like minus 1 times k? Where I'm simply saying I'm letting u of t, my input, be a combination of a scaled version of the state, minus kx of t, plus a scaled version of the reference input r. Now what I can do is I can actually combine terms that have similar multiplications of the state vector x. Or I can now write this as x dot of t is now a minus bk. There's the minus 1 coming in front of the b, and that allows me to subtract bk from a. That's times x of t plus bn r of t. And now what I've done is with feedback, I've now created a new system dynamics called f. Let me say f is now what I'm calling a minus bk. This is now my closed loop system matrix as opposed to the open loop system matrix, which was just a. By introducing full state feedback, I've now allowed myself to change the system's behavior from a to f, where f is now a minus bk. So how can I influence the system dynamics? By the selection of k. Let's go ahead and work through an example to hopefully make this a little bit more concrete. Suppose we now have, or are given, x is x1 dot, x2 dot, that's x dot, and A, our open loop system matrix that scales the state x1 and x2. Let's assign it to be 0, 1, 0, minus 1. And let's let our input matrix B be a column 0, 1. And if we wanted to, if somebody said, oh, what's the output y of t? I'm going to say my output is just going to be the first state variable component. Now, for those of you, and you've probably already taken ECE 310, I'm assuming, what are the eigenvalues of A? Can you tell me that without a lot of effort? you could compute the determinant of lambda I minus A, that matrix, or you could realize that, oh, if this is upper triangular or lower triangular, my eigenvalues are on the diagonal of this A matrix. This is an upper triangular matrix. There's nothing below the diagonal. It's 0. It's upper triangular. All the dynamical information is on the diagonal of this A matrix. That says then that the open loop eigenvalues of this system matrix A are at 0 and minus 1. A pole's at the origin and one's at minus 1. That's pretty consistent with what we've been selecting for systems all semester. Our open loop eigenvalues which are the lambdas of A, are at 0 and minus 1. And if I said, just as a review, do you remember your cheer? One of your cheers, can you now give me the open loop system in terms of state space matrices, A, B, and C? What is the transfer function g of s between the input u and the output y given A, B, and C? It's taken us all semester to learn our ABCs, right? No, but we now can use A, B, and C. We can't just say, oh, it's A, B, C. It's actually C times SI minus A inverse times B. If you're given A, B, and C, you can now find the transfer function between the input u and the output y. Doing that now is fairly straightforward. We have C, which was 1, 0. Luckily, A is not too involved, so we can now put S on the diagonal and subtract A from it, and A was upper triangular, so we don't have a lot of information coming into our SI minus A. We need to invert that and then multiply it by B. That will give us our transfer function, our open loop system, where g of s now is C, and we can form the inverse of a 2 by 2 fairly quickly. We can say, oh, that's 1 over the determinant, which is the product of the terms on the diagonal minus the off-diagonal terms product. Then for a 2 by 2, we can simply interchange the diagonal elements and change the sign of the off-diagonal elements. That's now the inverse of that matrix, where the 1 over that denominator is a scalar. It's a scalar in S, and we have to remember to multiply, post-multiply the result by our input matrix B. Let's now factor this piece out from everything so that now I have 1 over s times s plus 1. Since the second term vanishes, I'm multiplying by 0, times the C matrix, 1, 0, s plus 1, 1, 0, s. There's the SI minus A inverse, times the B. And now I simply have to multiply those 3 matrices on the right. I can do that many different ways. Suppose that I now multiply from the right side in, or I multiply first by the input matrix, or that now really is saying just pull off the second column in SI minus A inverse. So that's the almost there. We're going to end up with a scalar in our numerator, which is the product of 1, 0 and this vector 1s, which just pulls off the 1, or my g of s is now something fairly basic. It's now 1 over s times s plus 1. And where are the poles of that? Those better be the same as the eigenvalues of A, as a way to sort of check our work. Let me introduce a new concept that will allow you on the final exam, if I say, is it possible to move these open loop eigenvalues, let's say they're at 0 and minus 1, to some new location. Let's say minus 2 plus and minus j2. And without going through all of the selection of the K matrix, you can actually check the system's controllability. Is the system controllable? If you wanted a new word, big word, to be using this weekend, you can now use the word controllability. Is your system controllable? What's the system's controllability? Or, that's really addressing the question, what can be done by applying or using full state feedback? If the system is controllable, then you can move the closed loop poles wherever you want by the appropriate selection of this vector K, or this matrix K, the full state feedback gain matrix. To check controllability requires that we check how many linearly independent rows or columns we have in this controllability matrix. And the controllability matrix is created once you are given the input matrix B and the system matrix A. And you just start hitting B on the left with powers of A. And you just keep padding those in to make this controllability matrix as wide as you need it. And as wide as you need it actually depends on how many states you have in your system. You take A and raise it to the n minus 1 power, which in our example, if n was 10, then this controllability matrix would be B, AB, A squared B, all the way up to A to the n B. That many columns you would now concatenate together and say, okay, do I have 10 linearly independent rows or 10 linearly independent columns? You could do either one. They'll give you the same information. If you do, then this system would be controllable. Can we apply this controllability or create this controllability matrix from our example? Where our example now consists of A, B, and C. We're given the system matrix A, and we're given B, so we should be able to build the controllability matrix script C. And now it's just a matter of determining how many columns or times to scale A, or multiply A together. This will be B. Then we have AB. Then we have A squared B. You just tell me when to stop. A cubed B. I'm listening. Oh, I should have stopped. Where do I stop? Can I start erasing? What do I need to raise A to in this particular case? How big is Nevada? How big is little n in this system? 2. N is 2. And we just need to create the controllability matrix to a size that takes A raised to the n minus 1, 2 minus 1, so A to the first power. Our controllability matrix now just consists of these two terms in the controllability matrix. In our case, we have B, which was 0, 1, and A was 0, 1, 0, minus 1. That was A. And B was 0, 1. So what's AB going to be? Well, we multiply B on the right with A, and that's just going to extract or pull off the second column of A, which means now that AB, that product, is 1 minus 1. We're learning new words. Did you learn rank in 310? Okay, so you know what what's the rank of this script C matrix? What do I mean by rank if you don't remember what that is? Here I'm going to introduce a new notation. I'm going to say the Greek letter rho is what I will use to denote the rank of a matrix. What is the rank of this controllability matrix? Or the rank really says how many linearly independent rows or how many linearly independent columns do you have in this C matrix. And I hope it's clear that you have two columns that are linearly independent. They don't both look like 0, 1 or 0, 7 or 0, minus 2. The second column has a non-zero entry in the first component. So these are linearly independent columns or linearly independent rows. The rank of that controllability matrix is 2. We need that rank to equal n. In order for our system to be controllable. Now, there's an easier way than checking linearly independent rows and column if you think it's easier. If this controllability matrix is square, which it is in our case, and it will be if you have one input or B is a single column, if C is square, then we can find whether or not C is full rank by just calculating the determinant of that C matrix. And if we have a non-zero determinant on this controllability matrix, it could be negative. If it's non-zero, then our system is controllable. In our example, if we went back and calculated the determinant of this matrix, which was 0, 1, 1, minus 1, that was our script C. This is now the product of the diagonals minus the product of the off diagonals. The first term vanishes, but the second term gives us minus 1, which is not equal to 0. And that now allows us to conclude that C is full rank. So that's another way you could quickly check without having to say, oh, can I by inspection see that those are linearly independent, or do I need to do row reduction or whatever you want to do to try to find whether or not these columns or rows are linearly independent, or how many of them you have. Okay, we've now learned that our system is controllable. Cut to the chase, can we find the K to position our eigenvalues where we want them? To make an F matrix have eigenvalues that we want versus where they began with the locations in the eigenvalues of A. What we want to do now is use full state feedback to try to place the closed loop eigenvalues of this new system matrix F, which is A minus BK, let's just select some locations. Suppose arbitrarily we say, let's let one of those eigenvalues be at -5 and another one be at -10. That might satisfy our design specifications, whatever those happen to be. That means then that we would like our desired closed loop polynomial or characteristic polynomial to have roots equal to -5 and -10. We want our desired characteristic polynomial to have roots of -5 and -10. Let me call that desired polynomial delta sub d of s. To obtain those for roots, I can simply build that desired polynomial as a combination or a product of two linear factors. And I can now multiply that out, and I have s squared plus 15s plus 50. That's where I would like my closed loop characteristic polynomial to what I would like it to look like for the appropriate choices of my parameters in the K matrix, the full state feedback gain matrix. Let's now build F from A, B, and K. A was 0, 1, 0, minus 1. B was 0, 1. What does K look like in terms of dimension and elements or entries? How big is K? How many rows do we have in K? How many inputs do we have? 1. So K has to be 1, and it has to have as many columns as our state vector, which is 2. K is now 1 by 2. Let's put in 2 entries, and we'll subscript those K sub 1 and K sub 2. We now can create F, and I'll do it in a couple of stages. The top row of BK is all 0 because we had a 0 entry in the top row of B, but the bottom row is just now going to be a copy, since it's scaling by 1, of K. And now if I simply do the algebra, I have 0 and minus K1, and then I have 1 and minus 1 minus K sub 2 as my parameterized closed loop system matrix F, where it's parameterized by these unknown or yet to be determined coefficients K sub 1 and K sub 2. What we now can do is we can find the characteristic polynomial associated with this F matrix, and what does that look like? Well, that's just the determinant of Si minus F. Or if I use a vertical bar to represent determinant, I now have S times a 2 by 2 identity matrix, that's Si, and I now need to subtract F from that, and here's F that I just computed. Again, if I do the algebra inside the determinant brackets, I now have a matrix that's S, and in the 2, 1 entry, I have a K1. In the 1, 2 entry, I end up with a minus 1, and in the 2, 2 entry, I have S plus 1 plus K sub 2. And I want to find the determinant of that 2 by 2 matrix, and we know how to do that. Product of the diagonals minus the product of the off diagonals. Or I now have s squared plus 1 plus k sub 2s plus k sub 1. But in fact, I wanted to pick, or I want to pick, k1 and k2 so that that polynomial equals my desired polynomial. The desired polynomial has the roots of minus 5 and minus 10. Now I'm saying I want this to equal delta sub d of s, which was s squared plus 15s plus 50. That's what I want. And hopefully you can see that all I really need to do is now compare coefficients or equate coefficients between the two polynomials. If I now equate the coefficients, if I look at the S1 coefficient, that says that 1 plus k sub 2 needs to equal 15. And now I can solve, that's just one equation and one unknown. Now I can see that k sub 2 is 14. And if I compare the S0 coefficients, that says that k1 is equal to 50, and that's pretty easy to solve. It's already solved for us. So now I know what my input needs to be. My input is a linear combination of all of the states, and it's minus k x of t plus n r of t. But if we put that in our matrix form, k was 50 and 14, scaling x1 of t, x2 of t, plus n times r of t. Or, writing that out a little bit more detailed, that's taking the first state component, scaling it by 50, and subtracting that and making that part of u of t. Doing something similar by scaling x sub 2 with 14. And then we need to figure out how big do we make n to make this u of t completely determined. But if we now look at this in a block diagram form, we can create what we have in a block diagram structure. We have our original system. Let's do it in an all-integrator block diagram. There was our u of t, and that now takes x sub 2 and scales it by a minus 1, and it didn't do anything, or it took x1 prime or x1 dot, and that was equal to x sub 2, so this is now x1 of t, and that was just equal to y of t. So there's our original open loop system. But now we've put full state feedback around that. We made u of t equal to minus 14 times x sub 2 of t and minus 50 times x1 of t. And finally we said, oh, u of t can also have a scaled version of the reference input r of t. So there's a block diagram, an all-integrator block diagram of our closed loop system with full state feedback. The black is our original system. the blue is our full state feedback. Now we have two different variables, two state variables that we're able to measure, feed those back or scale those, and then allow those to create part of our input signal u of t. And we've now changed the dynamic behavior. In equations, we could say that we now have x dot of t is equal to a minus bk x of t plus bn r of t, and y of t is still c x of t, where this is our closed loop system. Can you now find from that the closed loop transfer function? Now this looks very similar to what you've maybe done before. Now you could say, oh, here is our system matrix, and here is a slightly different input matrix, B bar, but now we have our cheer, C times Si minus F inverse times B bar. And that's now our closed loop transfer function. That's T of S, which is the transfer function between the reference input R and the output Y. That's now C, Si minus F inverse B bar, which is Bn. And if we expand down, or if we parameterize F, this closed loop transfer function T of S is now C, Si minus, F was A minus Bk, invert that whole expression and scale by Bn. This is now our closed loop transfer function. And in our particular example, you could actually tell me what most of that is. Let me call that T sub C. T sub C of S is now, in our case, 1 over S squared plus 15S plus 50. That's because we selected K to give us those closed loop poles. And the only thing we have left to pick is N. And that's just a constant in this case. It's a 1 by 1 matrix, which 1 by 1 is a scalar. Suppose now I said I want a DC gain of 1 in my system, in the closed loop system. What does that imply I want T sub C of S to look like? Or what does that constrain on T sub C? Anything? At S equal to 0, this needs to equal 1. If I want this closed loop transfer function to have a DC gain of 1, then I'm saying that I want T sub C of 0 to equal 1, which in our case is 1 over 50 times N, and now we know what N is. Now we can pick N equal to 50. That will give us a DC gain of 1, and the U of T is now minus 50 x1 of t minus 14 x sub 2 of t plus 50 r of t. That will now produce a DC gain of 1 with full state feedback. And I might put in a few more details, but that's basically it for full state feedback with a reference input. And we'll pick up with comparing full state feedback with some of these other controller designs that we've done in the previous weeks.